Let's review how to solve beam problems. First, we write a sum of the forces equals 0 equation. Next, we choose a convenient pivot point where an unknown acts on the system. Then, we write a sum the torques is equal to 0 equation around that point. Thirdly, we solve the torque equation for the missing variable, then we'll plug that back into the force equation. We'll show you two more examples in this lesson. So here's our problem. Let's go ahead and draw the forces in with their positions. 300, 400, and 500 newtons act 3, 5, and 7 meters from the left end. The beam itself is 12 meters in length. So you can see here that 300 Newton force is 3 meters away, the 400 Newton force is 5 meters from the left end, the 500 Newton force is 7 meters from the left end, and the entire length of the beam is 12 meters. Again, we're going to neglect any mass of the beam, we're going to consider it negligible, and we want to find the reactions at A and at B. So let's write a force equation first. Here we have 5 forces. Reaction at A, reaction at B, and then 300, 400, and 500 newtons. A and B act upwards. These three act downwards. And we can just add them. 300 plus 400 plus 500 is 1200. A and B are upwards, so they're given positive signs. These three added together all point downwards, minus 1200. We can't solve that because it has two unknowns with only one equation. So now we have to write a torque equation, and we need to pick a pivot point that goes through one of our unknowns. So you could either pick here at A or at B. Doesn't make any difference. I've picked the point at A. So with regard to this point, 4 of the forces would have a non-zero torque about that pivot point. So the reaction at B times the distance that reaction B is away, 12 meters, minus the force times the lever arm for the 300 Newton force. And of course the 300 Newton force would cause the beam to rotate clockwise, and clockwise typically is negative, whereas the reaction at B would cause this beam to rotate counterclockwise if it had its way. Typically that's positive. So now we have force times lever arm for the 400 Newton force and force times lever arm for the 500 Newton force. Again, forces that would cause the beam to rotate clockwise are typically negative, and forces that would cause the beam to rotate counterclockwise are positive. That all adds up to 0, which means we can solve that equation for the reaction at B. It comes out to be 530 newtons. We're going to now plug that in to the force equation. In other words, RA plus 530 minus 1200 equals 0, which means that RA must be 670. If this beam had a weight, can you see that the beam is uniformly, evenly distributed between those two reactions? So of the 300 newtons that this beam would weigh, if it weighed 300 newtons, let's pretend, 150 of those newtons would have to be supported by RB, and 150 of those newtons would have to be supported with RA. So those would be the reactions. Let's try one more. Again, we're going to neglect the beam's mass. We're going to write a force equation where the ups equal the downs. So RA plus RB, those are both acting upwards, minus 210, minus 630, minus 850. All of that gives you a negative 1690, and that should all add up to 0. For the torque equation, we need to put a pivot point in there, and I'm going to choose right there to be the pivot point for two reasons. One, you need to pick a point that one of the unknowns passes through. So we're either going to pick right there where the green dot is, or we're going to pick over here to the right above reaction B. But I chose the reaction above A because that will not only knock out the RA component of the torque, but it'll also knock out the 630 component of the torque. So I won't have to consider either of those two forces in this equation here. RB would contribute a positive torque, RB times a lever arm of 7 in the counterclockwise direction, so that's positive. The 850 Newton force is 6 plus 7 meters away, that's 13 meters away, and can you see that if this green dot is the pivot point, that this 850 Newton force would cause the beam to rotate clockwise, which is negative. So force times lever arm in the clockwise or negative sense. And there's only one other force that we have to deal with, and that's the 210 Newton force, which will have a lever arm of 3, and will that sign be positive or negative? Well, how would that 210 Newton force cause this beam to rotate if it had its way? And it looks to me like that would cause the beam to rotate counterclockwise. So I'm expecting a positive sign. And those torques have to add up to 0. Again, we haven't had to use RA and 630 because the lever arms for those forces with regard to that point are 0. So we don't need to write those. Solve that for RB, 1490, and plug 1490 in right there. That'll give the reaction at A to be about 200. Now, if this beam weighed 600 newtons, you might say, oh, well, 300 of those newtons will have to be taken by reaction A, 300 newtons will be taken by reaction B. Not the case. And the reason for that is, of course, that this beam is not symmetric about those two reaction points. So we would have to take that into account in a different way in order to solve that.